Thank you. It's my honor to give a talk to celebrate the Maurício Peixoto's 90th birthday. And in my memories, he in the first time to introduce us how good a dynamic system can be. It's for differentiable dynamic system, it's called a structure stable. And today I will introduce another kind of good systems. This good is not for differentiable dynamic, it's for physical measures. Before I begin the talk, I would like to thank my friends and the professors in IMPA as I was a student here. This is my first time to give a talk in the conference of IMPA opened here. So the title is Geometric Structures for Physical Measures. Basically, what geometric structures? Basically, we would like to see the basins and the supports and the foliations, such kind of informations. First, let's give the definition of metric entropy. Okay, here we use SRB measure. So, an ergodic measure is called the SRB measure if its basin has a positive Lebesgue measure. Such kind of measure was first studied by Sinai, Roy, and Bowen for hyperbolic attractors. And later, Palis gave a conjecture. He asked if it's possible for any system can be approximated by another one, which having only finitely many SRB measures, and the basis cover a further bigger measure subset. Yeah, here we see the system. It can be maps or diffeomorphisms. So Bonatti and Viana, almost 15 years ago, yeah, they proved that for family of systems, they called differs with contracted center, they do satisfy the Palis conjecture. So here, when they wrote the paper, there is only one example. It's Manier's example. At that time, is a dA in T3. The example is like the following. You have a linear Anosov. A with 3 eigenvalues. This 3 was given by Manier. And then for this A, he do a modification, get a difference Fz. Fz is like following. In T3, we do a change in the neighborhood of a fixed point. We change the center direction. So here's the center direction. We change the index of the periodic point. And the outer side is the same with Anosov. Outer side F0 equal to Anosov. So basically for this example, and Manier proved that for this F0 is not hyperbolic anymore because outside center direction you have contraction. Here you have P has changed the index. It's not hyperbolic anymore. And Manier proved that this Fz is robust transitive. This is the first example of non-uniform, non-hyperbolic, robust transitive differs in T3. Okay, and Bonatti and Viana, they proved that this system, any C2 differs, such kind of differs, is mostly contracting. Oh no, they call it most contracting. Today we change to be called with contracted center. It's easy to understand. Why? Because in most of the region you have contraction. Only small part you have little expansion. So it's easy for us to see that this system has contracted center. Yeah. This was almost 15 years ago, the only example we know about the contracted center. But so it's quite surprising. now we have a lot of examples. And in fact, this kind of systems differ with contract center. We can go back almost 50 years ago, go back to Furstenberg. When Furstenberg studied co-cycle over random basis, in that case, he used a name called contracting in the fibers. In fact, we can see these two things are almost the same. So it's almost 50 years later, by Viana, they studied physical measure from another way, from another direction. We got similar things. So now this is the definition of difference with contract center. Difference with contract center is partially hyperbolic. Partially hyperbolic means the tangent space, you can split it to two continuous invariant bundles. One bundle is uniformly expanding. Another bundle is a little weaker. And our C2 partially hyperbolic differs, which has contract center. It implies for any U disk. Now, because here we have a uniform expanding five bundle, so we have strong unstable foliation. So basically, it looks like this. We have unstable foliation. In each disk, you always have some positive Lebesgue subset which has some contraction. So you will have the manifold here with no uniform size by Python theory. Okay. Positive Lebesgue in that leaf, in each leaf. Yeah, that definition is very technical. But we will show there are a lot of examples. Okay. So now let's briefly, before I give some new examples, I prefer to briefly record the no results. First is proved by Bonatti and Viana 15 years ago that any differs with contract center with some weaker contraction. It has finitely many physical measures and whose basin cover full Lebesgue measure subset. And so this system satisfies Palis conjecture. And now we would like to know what the measure looks like. You have finitely many measures, but the measure is very complicated. We would like to know what the measures looks like. So the support of the measures which saturate the unstable leaves. So we know that the support is good, looks like beautiful. And in fact, we can get more information recently is that the support of the different measures are separated. And in each support, it has a finitely many connected components. And in each component, the unstable manifold is minimal. So we have a picture like for. Okay. So the picture is like this. We have mu1, mu2. Here you have some support. The support is looking like this. You have several finitely many connected components, and in each connected component, unstable manifold is minimal. So each leaf is dense inside that connected component, and the F commutes these connected components. So at least for the support, we have good information on the geometry. This is already known, and quite amazing. It's proved by Martin Anderson that the difference with contract center is robust in C2, in C1 plus alpha topology. So give R differ with contract center, then we have a fine open set. And the number of physical measures is semi-upper continuous. So in particular, this implies to us if we have one differ with contract center, suppose it has a unique physical measure. Then in a neighborhood, every C2 differs has contract center with a unique physical measure because it's semi-upper continuous. Okay, so now let's keep in mind these results, and I will introduce some new examples. And This is count example. Before this is the main example we will study today. So before this, I would try to explain there are a lot of other examples. So the first example is Manier's example. Now I'll give the second example. Second example is given by Dogbiat. The Dogbiat, he proved that for the type 1 map of geodesic flow, for type 1 map of geodesic flow, after C1 bifurcation, then you will get a difference with contracted center. So this is a modification of type 1 flow, type 1 map of geodesic flow. So this is another example. And we also have this example is for volume preserving case. You consider 3-dimensional manifold. And we consider partially hyperbolic splitting. Here, partial hyperbolic means you have 3-dimensional. And you can suppose you have compact center leaf. You have a compact center leaf. So this is a partial hyperbolic difference with a compact periodic center leaf. Compact periodic center leaf. In this space, so this is an open set, because why? If you have compact periodic center leaf, it's normally hyperbolic. It's robust, you have this. And the volume preserving. We can show that in this set, exists C1 open dense set. Exists C1 open and dense subset R. Inside it, any C2 differ in R either is most has contracted center or inverse has contracted center. Any F in R, okay, C2. Either F or its inverse has contracted center. So this is a very big family. So for volume preserving, if you have compact periodic center leaf, then you can do bifurcation. You can always find contract difference with contracted center. These 3 kinds of examples we will not study today because which is simple. So today basically we will study 2 another examples. The first example is a count example. So yeah, the count example is not a difference. It's an endomorphism on cylinder. But we can do this on T3 for differs. But here the statement is a little simpler. So I prefer to show this example. So count example is like follows. The cylinder in the horizontal direction, we have uniform expanding, product 3. We have a uniform expanding in this direction. So because you are uniform expanding on the direction, you have 2 measures on the boundaries. We have 2 measures on the boundary because of which is uniformly expanding. We have mu0 and mu1. And for count example, he needed it's partial hyperbolic. So here we have strong unstable direction, horizontal direction, and here is center direction. Okay. And the count example, he needed the exponent of these 2 exponents to be negative. You can show, to do the integration, you can show the Diapolis exponent's center is negative. So we have, by Palis theory, we have 2 physical measures. We have 2 physical measures. No, this is union state manifold. Union state manifold by the absolute continuation. We have 2 physical measures. The most important thing for this count example is like following. One can check Here you have a periodic point P0, whose stable manifold is to here. And in the P1. In the low boundary, there is a fixed point P1, whose stable manifold is this segment. And by this, one can show that these two physical measures, mu1 and mu0, whose basis cover 4 Lebesgue measure subset, and the basin of each physical measure is dense. So the basin is like this. And we have this. Each one dense. And this property is robust. Robust means if you consider any f, say too small perturbation, if you preserve the boundaries, you will robust have this phenomenon. You will robust have two physical measures whose basin cover 4 Lebesgue measure subset, and the basins, each measure, the basin is dense. See, this is quite strange for us because the basin is always dense, right? Then Martin Anderson, he asked me one question in his thesis. What happens if in the boundaries? In the boundary, it's uniform expanding, so the measure is equivalent to the Lebesgue in the circle. So Martin Anderson, he asked me one question. The question is very interesting. If the differ, which does not preserve the boundaries, what happens? It is possible that two measures change to be one measure, or such kind of phenomena. In fact, this is this question has been asked a long time ago, almost as soon as this example was constructed almost 16 years ago. And people began to ask, well, it's strange, right? If you have two measures, one is above, one is below, basins each is dense, and then they always have this phenomenon. It's almost impossible. So people ask if it's possible that the two measures meet together to be one measure. So today I will show it's true. Basically, we will show that after this kind of perturbation, one measure disappears. It's true, one measure will disappear. And these things will be quite strange. So you have two measures, then immediately you have one measure. Where is another measure? I will explain later. Before answer Martin's question, we need to do some preparation. So let's keep this question in mind. So how in counting example, you have two measures, one above, one below, and the base is dense. And this is robust if you preserve the boundaries. How we will delete one measure if we change the boundaries. Okay, so basically this question is when a physical measure disappears. I will give a mechanism today. So, okay, this is an example for contract center because you have contract for the physical measures. And now let's show another example because I have explained there are quite a lot of examples for contract center. So this example has been obtained by Viana and me recently. So this is for skew product. So as I have said, we have the examples for contract center for DA, Magnet's example. We have a perturbation of time one map or geodesic flow, that's modification of flow. And I have said that we can do bifurcation for volume preserving, three-dimensional preserve compact periodic center leaf. And we have a count example. And now we have skew product. So we have a lot of examples to study. So this is skew product, C2. And so the first G is a transitive analysis of diffeomorphism. So M is short, we can suppose M is torus. We have G here. This is HX. No F. Because it's a little surprising in this case. Because why? Now circle, center bound is circle. How could you see that a circle contract? A circle image is still image, right? It's a little harder to think, it's contract. But it's quite amazing that is proved by Viana and me, that if F is skew product, we assume F is accessible. I will explain what means accessible. Then we have two cases. The first case is F has contract center. So each center leaf, and we can exactly see how many physical measures do we have. The number of physical measures smaller or equal to the periodic points in the complete periodic center leaf. It cannot be too many. The second case is a rigidity phenomenon, or it's a rotation. The second case is a rotation. If you have a rotation, you have a unique physical measure whose basis cover full big measure subset. Why the second case is a rigidity phenomenon? Because as soon as you have a hyperbolic periodic point, if you have a hyperbolic periodic point, it cannot be rotation, right? So in most of the cases, we have the first situation. It has a contract center.
You mean conjugate or rotation on the leaves?
Yeah, on the leaves. And the measure is the Lebesgue measure. This physical measure is equivalent to Lebesgue. This is a rigidity phenomenon. Anyway, we need to assume it's accessible. So I need to give a definition. What is accessible? Accessible is any partial hyperbolic difference is accessible if any 2 points can be connected by finitely many SU legs. And this is a C1 open and CR dense phenomena. We always have this. So basically this implies to us, in the skew product space, most of the C2 difference has contract center. And this is a little funny. Because why it's funny? Because we know I have said that with center we have circles. It's contract. So how would you say contract? Be circle to circle, right? And another thing amazing is that you can see the inverse. So F is contract. Suppose F is contract, its inverse is also contract. If F is contract, its inverse is also contract. So we have a difference. F has contract center, and its inverse can also have a contract center. Because why? Because this contract for the Gibbs U state, U direction. And its inverse is for S direction. This is a little strange. So now I will show another examples how physical measures disappear. How physical measures disappear, we will get a family of maps in the skew product. In the beginning, F0 is hyperbolic with 2 attractors. So we have 2 physical measures. And finally, in the F1, we will have a unique physical measure. And then during F0 to F1, it has a contract center. Because it has a contract center, you always have physical measures, always. So we would like to know what happens during the process. Because we have 2 measures, and then finally we have only 1 measure. So something happens. We would like to understand what happens. So the picture is like so. We have F0. We have F1. So for F0, we have 2 physical measures. SRB measures. 2. And because it's hyperbolic, it's robust. In our neighborhood, it's always hyperbolic. So in our neighborhood to F epsilon, you always have 2 physical measures. And from F epsilon to F1, it has a contract center. It's accessible. You have a contract center, so we always have physical measures. So the problem is that we have 2 physical measures, and finally, we have 1 physical measure. I don't know what happens here up to now. So, but there is one thing I would like to explain. Maybe people may be asking, it's not strange. Why not strange? Suppose you have 2 physical measures. The one measure shrink and shrink and shrink, right? And finally disappears. They change smoothly or continuous way. So this is normal. It's nature for us. It's not so strange. One shrink and disappears. But unfortunately, it's not in this case. Why? Because, as I said, the number for differs with contracting center, Martin proved the number of physical measures is semi-upper continuous. If it's semi-upper continuous, in the end, in one measure, the set with one physical measure set is open. So you will get these properties. You will get open set here. Each differs have one physical measure, but for Ft, the physical measure is larger than 1, Pz. Because the number is semi-upper continuous. So what happens is like this. In some point, you have 2, 3, or 4, maybe many physical measures. And in the next time, as soon as you change forward, change to one physical measure. Some measures disappear. We don't know what happened. So this is a little strange. And now we would like to understand what this happens. So first, let me give the construction of the example. Yeah, this is exactly what I said. So there is some time t0. For ft0, we have made several physical measures. And the next time, immediately, one physical measure. So they don't change continuously, in a continuous way. If you change, you have to immediately change. So this is a contraction. First, we contract f0. So for f0, we suppose the G is a transitive unknown solve, and for H0 is a most small. So we have a skew product. So H0, we have this phenomenon. It's most small. And so here we have Hx also. We have so for F0, it's a real skew product. It's a product. Because H0 is most small, so this system is hyperbolic. It's hyperbolic. We have two attractors. One attractor in the above, in the top, which is a torus. Another is in the low. So we have P1, P2, P3. Now I will change the difference. I will split in two ways. I split to two parts. I split this manifold to two parts. For the right part, now we will do bifurcation. So the second time, for T, quite small, we do bifurcation in the right part. In the right part, we get accessible. We can always do this, because accessible is C1 open, CR dense. We can always do this. So in the second step, here in this region, we get accessible. And then in the third step, we keep this unchanged. And what we finally get for F1 is like this. Here we get accessible. Right, we get 1. This is for F1. In the right, in the circle, we get only one fixed point. So this is the way how we get from F0 to F epsilon and to F1. So now I need to give a proof. Why? Finally, it has a one physical measure. Because, as I said, because you have accessible, and you have accessible, you have two cases. Remember, one is contracting, another is rotation. Because here we always have periodic point, hyperbolic periodic point, so it cannot be rotation. So it always has contracting center. So for T positive, we always have contracting center. And finally, and as I have explained, the number of physical measures smaller or equal to the numbers of periodic points in your compact periodic center leaf. Here you have one fixed point. Since we have only one fixed point, the number of physical measures has to be unique. So we have this picture from 2 measures to 1 measure. Okay, something happens. So now let's see why. Why we need to give some explanation. Why some measure disappears? Okay. So now I will give a graph structure. So what is graph structure? Graph structure has no any relation with measure theory. It's just topological information. It's from differentiable dynamic system. So a graph structure is a finitely many periodic points, which has a proper index. The index is equal to the dimension of center stable direction. But we need a topological information. It's any unstable leaf, it intersects with the stable manifold of the periodic points. So basically, the picture like following. P1, we have a stable manifold of P1. And P2, we have a stable manifold of P2. So unstable leaf, it will intersect at least one of these stable manifolds. This really has no any relation with physical measures. This was first studied by Bonatti, Diaz, and Uris. When they show the foliation for 3-dimensional transitive partial body differs to be minimal. And so it's not necessary to every partial body differs has a graph structure. Maybe it does not have. But if a differ has a graph structure, this property is robust. It's a C1 robust. It means if F has a graph structure, then any nearby differs which also has a graph structure. And this periodic point of G is a continuation of the periodic points for F. And for graph structure, I need to define a perfect graph structure. A perfect, what do I mean perfect? It implies between these periodic points from P1 to PQ, there is no any heterocanonical intersection. You cannot say that the stable manifold of one periodic point cannot intersect the unstable manifold of another periodic point. And it's easy to show that a graph structure, it always has a perfect graph structure. Okay, so now we come back to physical measures. Because for graph structure, it's just differentiable dynamic systems. If you give me a partial hyperbolic difference, suppose it has a graph structure, we can really use a computer or use some way to find it, where the periodic points. We can find it. It has no any relation for the physical measures. But Marcelo and shows that if a differs which has contract center, then automatically it has a graph structure. It has one. Okay. Now let me show the relation between graph structures and physical measures. First, the number of physical measures, suppose F has contract center, as Marcelo proved, it do have a graph structure. Then the number of physical measures equal to the number of elements in the perfect graph structure. And remember, the perfect graph structure is a topology information. It has no any relation with physical measures. So suppose you give me a difference. You say, let's say 2. You told me it's contract center. Then you ask me, how many physical measures do we have? What should I do? One way is you use computer to do calculation to see how many physical measures do we have. That's complicated. Maybe some measure you will miss, because the basin in general is a counter set. So now we use the dynamic topology information. We can calculate how many periodic points in our perfect graph structure. We can find it, and then we can show how many physical measures do we have. Okay. And each periodic point is contained in the support of a SRB measure. So basically, you give me one periodic point, it's contained in a physical measure. And what's more, it can explain to us a lot of things. So we would like to ask, where is the measure? We have a measure. Where is the measure? So the closure of the unstable manifold of the periodic points is the support. So give a graph structure, we know exactly where is the support. And I also would like to ask, where is the basin? Where is the basin of this measure? The basin of this measure, closure of the basin of this measure is equal to the closure of the stable manifold of the periodic points. So we don't need this example anymore. So suppose we have F, which has contracted center. Suppose we have a P1, P key is a perfect graph structure. So we have a P1. So how to get the first measure? The first measure is the support of the first measure is the closure of the unstable manifold of the periodic points. Okay, so now we know the support. So how the basin? Where appear the basin? Because in general, basin is very complicated. We don't know where it is. So we said the closure of the basin is equal to the closure of the stable manifold. So for this periodic point, we can see where is the closure, and we can exactly know where is the basin. So the perfect graph structure explains to us a lot of geometric information of the physical measures. And as soon as we find it, we can exactly know where the support, where the basin, okay, and how many number of physical measures. We don't need to use computer to calculate, to look, to check where is the measure. Okay, so in particular, we can see the number of physical measures is equal to the number of perfect graph structure. So now I will explain why in some cases some measure disappears. Because the number of physical measures equal to the perfect graph structure, suppose we have Fz. Then we will have a graph structure P1 Fz to Pk Fz. This is perfect graph structure. Suppose we have another D for F is near to Fz, C2 nearby. Because the perfect graph structure for Fz is a graph structure for F, because the graph structure is a robust property. So we get a graph structure for F. It's a continuation of P1F to PKF. The graph structure, you have the same numbers. But the problem is that the graph structure is maybe not necessary to be full perfect anymore. Because maybe you will get a heterokinetic intersection. So it's like this. The perfect graph structure of F maybe is contained but not equal to this one. In this case, we will lose one measure. Because the number of physical measures is equal to the perfect graph structure. So basically, why we lose measures? Because we get heterokinetic intersection between elements in a perfect graph. At first, you have a perfect graph, and sometimes you get the intersection here, and then one measure disappears. And this is the main reason. Here is if and only if. So now it's a time for us to come back to the Kant's example to introduce why in the Kant's example, if we don't preserve the boundaries, some measure disappears. So we have a counter example. So first let's see what's the perfect graph structure for this Fz. The perfect graph structure, you have two elements. So, okay. The perfect graph structure for Fz is two elements. You can check. One is P1, another Pz, another is P1. So this is the counter example. So now I do bifurcation. We do a bifurcation. Okay, we get an F. So the stable manifold of P, the answer manifold of Pz is like this. Right? What's the stable manifold of P1? Stable manifold of P1 is a preimage. Its preimage is everywhere dense. So exists some preimage of P1. It's a stable manifold to have an intersection here. Right? We get an intersection. So what happens is if we do a bifurcation in the above, if you don't preserve the above boundaries, then graph structure, I call this above. So we got F, PGS, it preserves the below boundary, the low boundary. This is F, preserves the low boundary, but not preserves the above. In this case, the perfect graph structure is element here. So we have one element in the perfect graph structure. So one measure disappears. One physical measure disappears. We have two measures to one measure. And it's very interesting because why? Let's see. We do bifurcation here. We don't do any change in the below. We don't do any change in the below. So in the below, you have the same measure as before. If you do bifurcation here, in the below, in the low boundary, the measure is the same. You don't do any change. So what happens is if you do a push above, the measure in the above disappears, but the measure below, you don't do any change. So, yeah, F has a unique physical measure in the low boundary. And in particular, the basin explodes. Why? Because for Fz, you have two physical measures. We have two physical measures. But for Fl, you have mu 0, mu 1 for F. But for Fl, you have mu 0. It has one physical measure, its basin explodes. And another measure disappears. Okay. Now let's do another bifurcation. If we change below, preserve the above boundaries, what happens? It's in a similar way. If you change here, preserve the above boundary, then you preserve the above measure, the measure below disappears, and the basin of the above measure explodes from half of the Lebesgue to global. It's quite strange, yeah? So, okay, so now let's see. How about we change both? We change both, it's much more interesting for us. If we change the both, that so here we have P1, here we have P2. If you change here, and you change here, so what happens? What happens is that they are homokinetically related. They are homokinetically related. Because P2 has a preimage, it has this intersection, and then P1 has a preimage, has this intersection. If you don't preserve the two boundaries, you have a homokinetic related between P1 and P2. So in this case, I call this is F, Okay, F star. For this map, the perfect graph structure of F star, it can be P1 or it can be P2 or P0. Okay. As I said, the support of a measure is equal to closure of unstable manifold of a periodic point. Now P1 and P0 is homogeneously related. So where is the support of the measure? The support of the measure, because it's homogeneously related and it contains an unstable leaf, it should be, and then come back. So if you don't preserve the two boundaries, not only measures disappear, bases explode, and the support of the bases explode. The support of the measure explodes because it's equal to the homogeneous class. So this is an application of graph structure to Kant's example. We can exactly see what happens in the process in the family of differs when a measure disappears, when its base explode, and when the support explode. And this is if and only if this is the unique mechanism for differs with contracted center has such kind of phenomenon. How many time do I have? Okay, I will quickly record the proof. So basically, is because every physical measure is a Gibbs state, and the Gibbs state has negative center near-space burden. We take a mu1 to mu to be the SRB measure of B, and okay, I will draw the picture proof like here. So we have a perfect graph structure, P1, P2 to Pk. This perfect graph structure. We have physical measures, mu1, mu2 to mu(n). The numbers may be different. We need to prove they are the same numbers. So by the Cartesian closing lemma, we can take a periodic point Q1, Q2, Qn, which has proper index. Index is the dimension of center stable direction. So we have the what we need to prove is that for any point here, you can find one of the Q which are homogeneously related with it. We can do this. Why we can do this? First, you can see unstable manifold of Q1, it has to be intersect one of the stable manifold. By the definition, it's graph structure. Any unstable leaf should intersect one of it. Suppose you have this one. So we get one directional intersection. How to get another one is like following. You take a disk here, you consider the Lebesgue measure restricted to it, you consider its iteration go forward for the Lebesgue measure, it will converge to one of the Gibbs state. Now, the sum of the or combination of the unique states, and then it will intersect someplace. But it has to be intersect this one. Because why? If you intersect another one by the lambda lemma, you can show the support of these two measures has to be intersect. That's a contradiction because we have shown differs with contracted center, the support should be disjoint. So we can prove that you have this phenomenon. 1 to 1. Since it's 1 to 1, and we know that support this is U saturated, you can show this point is exactly contained in the closure, in the support. So we have this picture. Okay, so we proved the number of physical measures and the number of perfect graph structures are the same. Since and this point is contained in the closure, because unstable leaf is dense in the support, so we proved the unstable closure or unstable manifold of the periodic point equal to the support. And the basin, okay, we still have time. So we know that we have mu1, we have P1. So we need to prove the basin, closure of the basin equal to closure of the stable manifold of P1. How to do this? First, like this. In the unstable manifold of P1, you take a disk. This disk is Lebesgue positive because of, in the assumption Lebesgue almost exists a positive Lebesgue subset which has negative Diapalis burden. So we have a contract by the Palis theory. This belongs to the basin of the measure. You use lambda lemma iterated go back. You can show that the basin will accumulate to the stable manifold of that periodic point. So another way, this is one way. Another way is like this. Suppose you have basin. Suppose you have basin of this measure, how the stable manifold converges to it. This is another problem. The way is like following. Near the basin, you take a U disk, quite small, very small, and you iterate it go forward. This disk will converge combination of U state which contains this measure. If you wear this disk D, you will see that F and D intersect with the stable manifold of P1. And then automatically pull back, you will show you have this intersection. So, by this, so basically, what I said today is our work is to try to understand the information of physical measures without do calculation. And we would like to exactly see how this measure change. We would like to see it, not only study. We would like to see what happens. So finally, we can really do it. So given difference with contract center, we can find a graph structure, which can become is a topology information, C1 robust. And each point, the unstable manifold closure, unstable manifold is support. The closure stable manifold equal closure of the basin. We can exactly see when the measure disappears, the support explodes, and the basin explodes. So this result strongly suggests that the difference with contract center should play an important role in the study of physical measures. And in fact, there are many other results I have no time to say today. We can obtain a lot of information of absolutely continuation for the center-bound center directions. And it also has many relation to the study of co-cycle. As I explained, it was began from Forsberg. Anyway, for study Diapalis burdens for radial co-cycles, and then 40 years later was studied by Bonatti and Viana for physical measures, but they are the same things. It's quite interesting. Okay, so thank you.